Hello everyone. Today I'll be discussing about transpose of a matrix. If given a matrix, we can obtain a new matrix by interchanging the rows and columns of the given matrix. So such a matrix is known as transpose of the given matrix. If A is Aij an m by n matrix, then the matrix obtained by interchanging rows and columns of A is called transpose of A. The transpose is denoted by A dash or AT. So that is, if A is an Aij, an m by n matrix, then A dash is equal to Aji, an n by m matrix. That means whichever the rows in A, that will become columns of A dash. For example, if A is a 3 by 2 matrix, that is 1 2 0 minus 1 3 4, then A dash will be a 2 by 3 matrix. Observe that first row here will become first column in A dash, second row in A will become second column in A dash, third row in A will become third column in A dash. Another example, if A equal to 1, 2, 3, that is a row matrix, then A dash will become a column matrix, that is column matrix 1, 2, 3. So here the A has, the order of A is 1 by 3, whereas order of A dash is 3 by 1. Another thing is that if an element 2, here the position of 2 is A12, that will become A21 in A dash, and similarly 0 is A21 element, that will become A12 in A dash. So in general, the element Aij in A will become element Aji in A dash. That is, the position of row and column will get interchanged in A dash. Now next is properties of transpose of the matrices. That is, for any matrices A and B of suitable orders, we have A dash dash, that is transpose of A transpose. So if you take the transpose of A transpose, it will become A. For example, A dash dash whole dash will become 1 2 3, that is same as A. So here A equal to 1 2 3, that is row matrix, A dash is a column matrix 1 2 3. So if you take the transpose of A dash again, it will come back to A, that is the first property. So A transpose whole transpose is equal to A. Second one, Ka whole transpose, that is scalar multiple of a matrix, the transpose of that will be K times A transpose, where K is any constant. And third one, A plus B whole dash is equals to A dash plus B dash, that is transpose of sum of two matrices is sum of the transposes. The fourth and final property, that is AB whole dash, that is transpose of product of two matrices, is equal to B dash A dash. Note the difference here, that is the product of the transposes, that is equal to B dash into A dash. It's not A dash into B dash, it's AB whole dash is equal to B dash into A dash. These properties can easily be verified with examples. So for the matrices here, the next is an example to verify the fourth property, that is, if A and B are given matrices, verify that AB dash equal to B dash A dash. So here A is given as 1 minus 4 3, B is given as minus 1 2 1. So we have to verify that AB dash equal to B dash A dash. So first we will find AB. AB, that is, you need to find the product AB. So here A is a 3 by 1 matrix and B is a 1 by 3 matrix, so that the product AB will be a 3 by 3 matrix. So after finding the product AB, you need to find the transpose of AB. That is, you just need to interchange the rows and columns of AB. So first row in AB will become first column in AB dash. Second row in AB will become second column in AB dash. Third row in AB will become third column in AB dash. After finding AB dash, now you need to find B dash A dash. That is, B dash is transpose of B. So here B was a row matrix, that will B dash will become a column matrix. Similarly, A was a column matrix here, so A dash will become a row matrix. So now you need to find the product of B dash A dash. So B dash, so here B dash is a 3 by 1 matrix and A dash is a 1 by 3 matrix. So that B dash A dash will be a 3 by 3 matrix. Now from B dash A dash and AB dash can see that both these matrices are equal. That is, AB dash is equal to B dash A dash. Now we move to another example, that is, find the values of x, y and z if the matrix A, that is 0, 2y, z, x, y minus z, x minus y, z satisfy the equation A dash A equal to I, where I is the identity matrix. Since A is a 3 by 3 matrix, I is an identity of 3 by 3, or I is an identity matrix of order 3. So A is given as 0, 2y, z, x, y minus z, x minus y, z. So A dash will be the transpose of A, that is just obtained by interchanging rows and columns of A. So if A equals to 0, 2y, z, then A dash will be 0, 2y, z in first column, x, y minus z in second column, x minus y, z in third column, and we multiply with A, that is 0, 2y, z, x, y minus z, x minus y, z is equal to identity matrix, that is 1, 0, 0, 0, 1, 0, 0, 0, 1. If we multiply A dash and A, the first row will become 2x square. If we equate with the right hand side, that is the identity matrix, it will become 1. So 2x square equal to 1. So that x is equals to plus or minus 1 by root 2. Similarly, if you multiply the second row and second column here, so you will get 6y square. So that is equal to 1 from RHS. So 6y square equal to 1. So y is equals to plus or minus 1 by root 6. Similarly, third row and third column here, it will give you 3z square equal to 1. So z is equals to plus or minus 1 by 3. Here you need not multiply all the elements of the matrices. Here you can verify the other elements to be 0. For example, if you take first row, second column, so you multiply element by element, so it will become 0, xy minus xy, so that is becoming as 0. So all other elements will be becoming 0. So you need to verify the diagonal elements of, since the diagonal elements of the RHS is coming as 1, 1, 1. So to get the diagonal elements on the left hand side, you need to multiply first row, first column, then second row, second column, similarly third row, third column. So that 3 will give you the values of x, y and z. Next is, using transpose of a matrix, we are defining two types of matrices, that are symmetric and skew symmetric matrices. A square matrix A equal to Aij is said to be symmetric if A transpose equal to A. So a square matrix is said to be symmetric if its transpose is same as itself. So that is A dash equal to A. So if you interchange the rows and columns of A, there is no change in the matrix. Such a matrix is known as a symmetric matrix. That is Aij equal to Aj for all possible values of I and j. So for example, if A is given as 1 minus 2 3 minus 2 4 0 3 0 5, so when we find the transpose of A, that is A dash, we can see that it is also coming as the same 1 minus 2 3, that is first row becoming first column here, then second row minus 2 4 0, that is becoming second column here. Similarly 305, that is third row becoming third column here. So it is a symmetric matrix since A dash equal to A. So if you observe that a matrix will be symmetric if A12, that is this element A12 should be same as A21, so that when we interchange the rows and columns, these two will remain the same. Similarly, A13 should be same as A31. A13 and A31 are same here. Then A23 should be same as A32. If these three elements are same, then only the matrix will become symmetric. These pair of elements, that is A12 and A21, A13 and A31, A23 and A32, if these three pair of elements in a 3 by 3 matrix are same, then only it will be a symmetric matrix. And you can see that the diagonal elements for a symmetric matrix can be anything, because when we find the transpose, the position of the diagonal does not change. So it's very easy to verify whether a given 3 by 3 matrix is symmetric or not. You just have to verify these three pairs of elements, that is A12 and A21, then A13 and A31, then A23 and A32. If these three pairs of elements are same, then it will be a symmetric matrix. Next one is a skew symmetric matrix, that is a square matrix A equal to Aij is said to be skew symmetric if A dash equal to minus A, that is transpose of the matrix is equal to negative of the given matrix, then such a matrix is said to be skew symmetric matrix. For example, if A equals to 0 minus 2 3, 2 0 minus 1 minus 3 1 0, this will be a skew symmetric matrix, because if you write A dash, so if you write A dash will be 0 2 minus 3 minus 2 0 1 3 minus 1 0. Now if you compare it with A dash is negative of A, so if you multiply all the elements of A with minus 1, you will be getting A dash. So A dash is equals to minus A. So because of this A dash equals to minus A, we can say that A is a skew symmetric matrix, that is Aij equal to minus Aji. So Aij equal to minus Aji for all possible values of I and j. So from here you can observe that, like in the case of symmetric matrices, the three pair of elements, that is A12 and A21, this should be negative of each other. So if A12 is minus 2, A21 should be plus 2. Similarly, A13 and A31 and A23 and A32, these three pairs of elements should be negative of each other. And one more important properties of skew symmetric matrices, that is about diagonal elements. So skew symmetric matrices are A dash equal to minus A. So A dash is equals to minus A. So if you change the position of the diagonal elements, that is, if you find the transpose, the position of the diagonals will never change. So the diagonals will remain in the same position if it is transpose or given matrix. The diagonal elements will be in the same position. There will not be any change in the position of diagonal elements. So because of that, the diagonal elements of a skew symmetric matrix has to be zero, or zeros. Otherwise, if you change the diagonal elements are non-zeros, then a dash, it is not possible that a dash is equals to minus a. So we can easily prove that a square matrix A equal to Aij is said to be skew symmetric if A dash equal to minus A. So that means Aij equal to minus Abi. Aij equal to minus Abi for all possible values of I and j. Now if we put I equal to j, we will be getting diagonal elements. So that is Aii equal to minus Aii. So therefore 2aii equal to 0, or aii equal to 0 for all i's. So I'll repeat again, all the diagonal elements of a skew symmetric matrix are 0. So this is a property of a skew symmetric matrix, that is its diagonal elements are 0. So again I will repeat, a square matrix is said to be symmetric if A dash equal to A, that is A dash equal to its A transpose equals to itself, and a square matrix is said to be skew symmetric if A dash equals to minus A. So now we'll go for an example. So here, given that A and B are symmetric, you have to prove that AB minus BA is skew symmetric. Given that A and B are symmetric, you have to prove that AB minus BA is skew. So we need to prove that the transpose of AB minus BA is equal to negative of itself, that is minus of AB minus BA. So AB minus BA transpose will take, so using the property of transpose we can split, that is transpose of difference, we can write it as AB transpose minus BA whole transpose. Now using AB transpose equal to B transpose A transpose, we can write AB transpose as B transpose A transpose. Similarly, BA whole transpose is equal to A transpose B transpose. But given that A and B are symmetric matrices, so that means B dash equal to B and A dash equal to A. So B dash equal to B and A dash equal to A, that is substituted here. So this will become BA minus AB because A and B are symmetric matrices. So now if you take negative outside, it will become minus of AB minus BA. So we got AB minus BA whole transpose is equals to minus of AB minus BA, that is negative of the given matrix. So the conclusion is that AB minus BA is a skew symmetric matrix. Now there are two theorems which we will be using to prove that a square matrix can be expressed as sum of a symmetric and skew symmetric matrices. So before we move to that important theorem, there is one simple theorem. So given any square matrix A, with real number entries, A plus A dash, that is sum of a matrix and its transpose, is always symmetric irrespective of what is A. A can be any square matrix. So A plus A dash is always symmetric matrix and A minus A dash is skew symmetric matrix. So this can be easily proved. So if you take B equal to A plus A dash, we have to prove that B is symmetric. That means we have to prove that B dash equal to B. So we will find out B dash. B equal to A plus A dash. So B dash will be the transpose of A plus A dash. So now using the property that A plus B dash equal to A dash plus B dash, we can write this as A dash plus A dash whole transpose, that is A dash whole dash. So again a dash whole dash is equal to a. So this we can write it as a dash plus a. Since matrix addition is commutative, we can write it as a plus a dash. So now this is same as b. So now we got b dash equal to b. So we can say that b equal to a plus a dash is a symmetric matrix. Now to prove that A minus A dash is skew symmetric, so let C equals to A minus A dash. Now we want to prove that C dash equal to minus C. So using all the same arguments as in B, so we can write C dash, that is A minus A dash whole dash, which is same as A dash minus A dash whole dash, that is taking transpose individually. And again A transpose whole transpose is equal to A. So applying that also, we'll be getting A dash minus A. So now this, if you take the negative outside, will come as minus of A minus A dash. So that is equal to minus C. So C dash is equals to minus C. So therefore we can say that A minus A dash is a skew symmetric matrix. So what does this theorem says that given any square matrix A plus A dash is always symmetric and A minus A dash is skew symmetric. So you can verify this with this example. So here A is 1, 2, 3, 4, that is it is a random square matrix, and A dash will be the transpose of that, that will become 1, 2, 3, 4. Now if you add these two matrices, you will be getting a symmetric matrix, and if you subtract A minus A dash, you will be getting a skew symmetric matrix. Now we move to the next theorem, which is very important and useful theorem, that is any square matrix A. You are given a square matrix A, it can be expressed as the sum of a symmetric matrix and a skew symmetric matrix. So given any square matrix A, we can write it as a sum of a symmetric matrix and a skew symmetric matrix. Any square matrix A can be expressed as a sum of a symmetric matrix and a skew symmetric matrix. So that means a square matrix A can be written as P plus Q, where P is symmetric and Q is skew symmetric. So what are the values of P and Q that is obtained from the previous theorem? Previous theorem we have proved that A plus A dash is symmetric and A minus A dash is skew symmetric. So if you take half of A plus A dash and half of A minus A dash, half of A plus A dash as P and half of A minus A dash as Q, and if add both of them, then we will be getting A. Here the half is taken because then only we'll be getting A. Directly adding A plus A dash and A minus A dash, we'll be getting 2A. So but we need A. So to get A only, we have taken half of both the matrices, that is half of A plus A dash, half of A minus A dash. So since A plus A dash is symmetric, half of A plus A dash is also symmetric and half of A minus A dash is skew symmetric. That is just for any matrix A, the scalar multiple, again using the properties Ka whole dash equal to Ka dash. So half of A plus A dash and half of A minus A dash are symmetric and skew symmetric respectively. So A can be written as half of A plus A dash, that is a symmetric matrix, plus half of A minus A dash, that is a skew symmetric matrix, and the sum of it is coming as A. So we have expressed a given square matrix A as sum of a symmetric matrix and a skew symmetric matrix. So given any square matrix, we can represent it as P plus Q, where P is symmetric and P equal to half of A plus A dash, and plus Q, where Q is equals to half of A minus A dash. That was the last part of this topic. Now we'll consider two examples, that is how to express a given square matrix as the sum of a symmetric and skew symmetric matrix. So here a matrix is given 3, 5, 1, minus 1. So let A equals to 3, 5, 1, minus 1. So you will find out the transpose of A, that is interchanging rows and columns of A. So it will become A dash will become 3, 5, 1, minus 1. Now we have to write A as P plus Q, where P is symmetric and Q is skew symmetric. So P is given by half of A plus A dash. In theorem 1, we have proved that A plus A dash is symmetric. So half of A plus A dash is symmetric. So now half of the sum of the matrices A and A dash. So that will come as half of 6, 6, 6 minus 2. So P we got it as 3, 3, 3 minus 1. Now we have to check whether P is symmetric. For that we have to find out P dash. So P dash is coming as P. So P is a symmetric matrix. Now to find Q, a skew symmetric matrix, that is half of A minus A dash. So if you find half of A minus A dash, you'll be getting 0, 2, minus 2, 0. Then to check whether Q is skew symmetric, so you have to find out Q dash. So that is Q dash is equals to minus Q. So Q is skew symmetric. So finally we got P and Q. Now we have to check whether P plus Q actually gives us A. So P we found half of A plus A dash, Q we found half of A minus A dash, P we got it as 3, 3, 3 minus 1, 3, 3, 3 minus 1, and Q as 0, 2 minus 2, 0. Now P plus Q. So P plus Q will give you 3, 5, 1 minus 1, which is same as A, the given matrix A. So now what we have done, we have expressed A. A is represented as a sum of a symmetric. What is that symmetric matrix? P, and a skew symmetric matrix. So we'll consider one more example, that is a 3 by 3. The method is same only. So a given matrix A. So let it be A. So you find A dash. Then we will find P. P is half of A plus A dash. So half of A plus the transpose. When we add both, we'll be getting this matrix. This is P. And we can easily verify that P dash equal to P. So P is a symmetric matrix. Now to get Q, Q is equals to half A minus A dash. So that will come as 0, 5 by 2, 3 by 2, and so on. So now you can verify that Q dash equals to minus Q. So Q is skew symmetric. Once you get P and Q, the only thing left to be verified is that P plus Q is A or not. So when we add P and Q, this is actually the given matrix A. So P plus Q will come as A. So that means we have represented A as a sum of a symmetric and skew symmetric matrix. Now any given square matrix, P is always equal to half of A plus A dash, and Q is equals to half of A minus A dash, and P plus Q will be always equal to A. So any given square matrix, we can express it as a sum of a symmetric matrix and a skew symmetric matrix. So that's all about transpose, its properties, symmetric and skew symmetric. Thanks for listening.